Hello, my name is Diego Maldonado, and I'm my group's representative for this UTA Discover Symposium. And the project title for us is Comparing Machine Learning and Deep Learning Models for Skin Lesion Classification. The summary of our project is that we want to compare the performance of deep learning models and machine learning models on a highly imbalanced and small skin cancer dataset, since it reflects more realistic healthcare conditions, and it also can highlight the limitations of current deep learning models where they're black boxes and it's difficult to ascertain what features specifically go into the final predictions, and also their inability or their constant struggle with training on small data sets. So our primary research questions are: can machine learning models achieve similar performance or better to machine deep learning models? And what features actually are the best at separating lesion types? So our dataset consisted of 23,057 images from ISIC, divided between 9 classes. And as you can see, the classes are highly imbalanced, ranging all the way from almost 500 images down to less than 100. For pre-processing on the deep learning side, we removed hair follicles, resized and recropped, and normalized the pixel values. As for the machine learning side, we also removed hair follicles. In addition to that, we converted the images into tabular features based off of color, texture, edge counts, and also added engineered features based on dermatology criteria, such as asymmetry, border, color, and diameter. Down here is a general workflow of our project, from removing hairs to splitting the data to resizing, recropping, and feature engineering, and then training and making final predictions. These images on the left show what parts of the images that the neural network is learning from the most, and how it got this top image incorrectly. It guessed it as melanoma instead of severe keratosis, but on this bottom one is one of the types it got correct, which correctly determined it was vascular lesion, and this shows what areas of the image it was learning from. On the right, this highlights our imbalance issue and the difficulty of training with the neural network, where it was mainly capturing only the majority classes. It completely missed our smallest class here, and also was missing most of the cases in our smaller classes, such as in here and in here. The best performing machine learning model, the XGBoost, performed slightly better, capturing a little bit more of the minority classes. On the bottom here, we'll see SHAP importance charts, and this essentially shows what features contributed the most to predictions. And as you can see, our engineered features, such as radius, area, height of the lesions, were actually the most predictive, which is highly useful for us and for future work. And our total conclusion is that classical machine learning models actually achieve competitive performance compared to deep learning neural networks. As you can see here, the macro F1 score of our best performing machine learning model was 50% and an accuracy of 60%, compared to just 45% macro F1 score of the MobileNet V2 model and the 55% accuracy of the MobileNet V2 model as well. And as I stated earlier, the engineered features inspired by the clinical dermatology tools proved the most effective predictive features, and it also highlighted that the class imbalance was the biggest bottleneck in our project. And it also highlights the need for good quality data and how data quality and data availability can be the biggest limitation in projects such as this. As for future work, we want to add additional texture features to account for finer detail in the lesions. We want to explore some more advanced models to see if they could provide additional power that we need. And we also want to try additional imbalance techniques, such as oversampling, undersampling, and data augmentation. And our final goal for our project is to be able to deploy a model and test it on sample images from the internet to see if it's generalizable. And thank you so much. This is our project.